Welcome everyone to today's GOCC. It's my pleasure to introduce to you Benjamin Decker. No, that was wrong. Let me try again. Benjamin Decken.
Yes.
But before I hand the stage to him, let me remind all of you of the community statement with the 3 guiding principles. We all have something to contribute. No one has all the answers. And please feel invited to ask questions. And with that said, it's my pleasure to introduce again Benjamin Decken from UCAM,
Yes.
who will talk about the new family of bijections between non-nesting partitions and non-crossing partitions. The stage is yours.
Thanks, Stefan. And thanks to the organizers for allowing me to talk about this work, this really nice work. And I would like just to say that this colloquium is really nice, even if I'm not here all the Tuesdays, but that's really nice. I'm just following the recordings, but I'm really it's really great. So let's start with this new families of bijections. So there are a bunch of people working with this thing. So 3 guys, Gabriel Frieden, Alessandro Irassi, and Florian Schreier-Aigné, who were postdocs in LACIM, in the laboratoire d'algèbre, sorry. And Nathan Williams.
A short tip, technical difficulties. So I think your connection was gone for a second, but I think okay. You were just saying about the archive and
I'm sorry because I was someone was calling for me, so that's okay.
Okay.
I'm just telling you what were the authors. So the 3 first were postdoc in LACIM, and Hugh Thomas, who is my supervisor for my PhD, and Nathan Williams, who joined the work at the end of this. That's a really nice work. So here is the figure for today. And I will try to explain all the things in these figures. So you see NC of SNC, which will be the non-crossing partitions for type A, and with the parameter which will be introduced just after. Then some actions called Creveras and Proveras. I will define it later. And the charm bijections. So nice things. So charm bijections between non-crossing and non-nesting partition. Here is the plan for today. So introducing all the things we need to understand bijection, and then I will try to introduce you the bijection, and if I have enough time, I will try to explain how was the strategy to prove the nice behaviors given by this bijection. So first, Coxeter elements. So here for all the talks, I will work with the Veil group called SN here. So AN-1 type group. So I will denote S1 to SN-1 all the adjacent transpositions. And first definition, a Coxeter element is an element obtained as a product of the following form. So just a product of all the adjacent transpositions, and all the adjacent transpositions have to appear exactly once. So you have here 2 examples, an easy one first, and a second one, less easier. And you can just see that the 2 examples give you a long cycle on SN, and that's exactly how we can characterize them. And it's a bit more than just saying that it is long cycles, but in fact, Coxeter elements are long cycles in the following form. So you see that you have a sequence starting from 1 and then increasing to some WM, let's say, and from WM you decreasing again to reach out 1 again. So we will define the left part and the right part of each coxet element as the first element of the sequence, just increasing, and then the decreasing part will be the right part. So again, the two examples just to understand what it means, everything, okay. Now I will here just give you all the positive roots of Sn. I will not define it in a general case, just to make sure that everything are in the same page. So positive roots, poset of n-1 type, sorry, denote phi n plus is a set of positive roots. I will denote it as transposition because there are bijections between them, and they are endowed with this order. So they are endowed, sorry, with an order defined with this cover relations. But of course, this definition is kind of messy, so it's more beautiful with a picture. So here you can see how it works for the poset of A8. So you have all the poset and all the, so the poset is from the minimal one at the bottom and at the top the bigger one, and the minimal ones will be called the simple roots. Okay, so they are the adjacent transposition, in fact. And then I will make some link with a bit of representation theory. I will not go too much far in this thing, but I will just say some little things that could be interesting to know and that could have really a nice use in this in the understanding of all the things. I will explain it here. So if you take a coxet element, you can define a realization of a coxet element, just an oriented graph, call it technically a quiver, and all the vertices are the adjacent transpositions, and then you put arrows between transpositions Si and Si plus 1, and you oriented the arrows just following the order in which you read it. Okay, so for the first example, the cycle 1 to 9, you will have this orientation of the quiver because you have 1 2, which will be before 2 3, and then before 3 4, and so on. And the second one, an example more difficult, but that's still you can see. Maybe try to explain the next result, because the next result saying that we have. So maybe just I will show you first. The next example saying that we have a one-to-one correspondence between coxet elements and orientation of the quiver of type A(n-1). Here I go back to the example just to explain how it works. So first you put 1 2, okay, you start with 1 2, and then you just see in the cycle what is the next image. So the image of 1, and you see that the image of 1 is 3. So between 1 2 and 2 3, you need that 2 3 is before 1 2, because if it's after 1 2, you will not have the image of 1 being 3. Okay, and you can go with some kind of algorithm like that. At each time, you ask yourself if you have to put it before or after each transpositions, and it works really well. So it gives us just a quick enumeration of coxet elements, but we can do it with other things. So first with the orientation, but we can also do it by just saying what are the elements in the left part or in the right part of the coxet of your coxet element. Okay, and then a more technical thing, again linked to representation theory. So again, take your coxet elements, and the Auslander right-hand quiver of your coxet element will be defined as follows. So you have the vertices which correspond to the transposition ij, and the rows going in these following rules. So you do the image of one of the two elements of your transposition, and you have just to make sure that the order is still in the same way. So you have I less than j, then either ci of c of I have to be less than j, or I have to be less c of j to make sure that you have the two arrows. Okay, so this definition is actually a combinatorial construction of the Ostrander-Ruyton quiver, of the quiver we saw just before. And some little things, again, linked to representation theory. We have indecomposable modules, corresponding to the transpositions, and the arrows corresponding to irreducible morphisms between them. And the Ostrander-Ruyton quiver gives us another poset structure over transpositions of SN. That could be also a really nice tool. So here you have an example, and you can see a bit how we could try to construct it. You have first to research what are the transpositions that you can put it on the left most side, that corresponding to the sinks. To the sinks of the quiver, QC, okay, and then from the sinks you can go at each step just applying C. So for example, this arrows 2 3 to 1 3. It's because the image of 2 is 1, okay, and then the image of 3 is 4, so it gives you the other row, and so on. And you have another rule that could be nice to calculate it, which is called the knitting rules. So you can see that for this square, you have 2 3 2 4 1 3. So to guess what is the element, you have to put it here. You can see that 2 3 is already there. So 2 and 3 on the top and on the bottom of this square are already taken, and then you take 1 and 4 that are not already here, and it completes the square. So that's there is a lot of ways, really nice to calculate the Ostrander-Ruyton quiver, but here I just give you one, try to explain it a bit. So now I will go more in combinatorial things. So first I will talk about non-crossing partitions, and here I will talk about it in type A. So fix your set of elements I1 to n, and a set partition will be said to be C non-crossing partition, a C non-crossing partition. So you fix also a coset element, if and only if you will not have a quadruplet that satisfies this thing. And more visually, you can see it like you can think about usual non-crossing partitions, but you labeled the element of your cycle just following the coset element. Okay, so you label the elements 1, 2, 1, 3, 4, and so on. Okay, and then you put your partitions again. So that's really really visual thing. More easier to understand than the definition itself, but okay. So a nice remark to make is that the C non-crossing partition can be seen as elements of the interval 1C of Sn if you see Sn endowed with the absolute order. So I remind you the absolute order, and that means that you can associate to any C non-crossing partition a permutation, and this permutation you can get it by taking all the blocks and just read all the element of your blocks following the counter, if I'm not mistaken, but following the counterclockwise orientation. So you can see for the triangle 1, 8, 6, and so on. Okay, so we will denote NC of SNC, the C non-crossing partition, and already a first nice result is that the number of them is the Catalan number. Some links with representation theory. I hope it will make you will have a little smile by seeing that there are links with cluster algebras for those who have already heard a bit about it. And then there are a lot of other links with representation theory. So I give you a reference, Ingalls and Thomas of 2008. But there are a lot of works behind, so you have all the elements, all the people, sorry, who are just below the slide. Maybe I can say something about just you have a link with elements of the Cambrian lattice. That's also something interesting, and non-crossing partition. So all the elements are in bijection, and some of them can be generalized to affine Deakin type. And that's really a nice links that could be if you never see it before, or if you want to learn a bit about representation theory, that could be a nice beginning to make. So now I go with the Creveras complement. And so the Creveras complement is defined as follows. You take again a non-crossing partition, and the C Creveras complement is by calculating pi minus 1 times C, if you see pi as a permutation like I explained before, okay? But you can calculate it more easily thanks to these pictures. So you can see that first you take a non-crossing partition, then you rotate it a bit. So you put the labels like you can see 1 bar, 3 bar, and so on in between all the elements. So it's like you rotate a bit the labels of your non-crossing partition, and then you will draw the biggest non-crossing partition you can draw, such that so it's in green here, such that it doesn't cross the red part. Okay, so if you do that, you will get the Creveras complement of your partition, non-crossing partition. Okay, so here, if you want to do and to verify that, you can do the calculation from the permutation thing. And if you do that, you will get exactly all the blocks I got. So for example, I will go back to the slide before. For example, 1, 7, 9, 3, 4, and 2, 6, 5. You can see again 2, 6, 5, 1, 7, 9, and 3, 4. So that works pretty well. And we can, thanks to this visual pictures, you can see that applying Creveras complements, if you apply it twice, you will get it the same C non-crossing partition, but it will be rotated just a bit. In fact, with this angle, and thanks to it, you can just say that the order of Creveras complement will be 2 times n. Sorry. Okay, so I will now go to the non-nesting part. If maybe there are questions, or I don't know, maybe that it's a good place if some people have questions. Nobody. I go ahead. Okay, nice. So non-nesting partitions. So the non-nesting partitions, here is the first definition of a non-nesting partition. So you take a partition and it will be said to be non-nesting if you avoid some configuration. So like a rainbow configuration, we can say it like that visually. So you don't, if, for example, if you have one in your picture below, if you have 1, 4, or maybe it's nice to with a 3, 6. For example, if you have 3, 6, you don't have 4, 5. Okay, because if you have 4, 5, it will be nested. Okay, so and 4, 5 have to be in a different block if it is not non-nesting. So here you have an example, a nice example, and just to make things really quick, because I will not explain more things about non-nesting partition, but I will see it more as ideals in the poset I give you in the beginning, the root poset C as a triangle one. So you can see it as just So any non-nesting partition can be seen as just taking an ideal of this poset. That's pretty nice. And here you can see the same non-crossing, non-nesting, partition corresponding to the ideal. And you can see that you can have all the elements that are non-comparable. Yes, I really okay, incomparable elements. So you can get it from the non-nesting partition. So that's pretty nice. And thanks to this bijection, you can have a bijection from non-nesting to deep path. Okay, to get the deep path, you just have to take the path over all the non-nesting partition. Okay, and that's it. So you have a link between those, and again, you can see that the non-nesting are counted by Catalan. Again, there exists already a bijection between, that's not again, but there exists already a nice bijection between non-nesting partition and non-crossing partition, just saying that if you want to have the non-crossing partition from that, you try to apply, each time you have a crossing, you try to uncross it. So like rotating it's visual, it's really visual, but each time you have a crossing, you kind of uncross it, and you will get a non-crossing partition like that by uncrossing point by point, and that works like that. But here I want to construct a bijection such that it preserves the Creveras action in the C non-crossing partitions. So it's kind of trying to translating the action of Creveras into something else in the non-nesting partition part. And that's how the Creveras complements appear. So first, before explaining what is the Creveras complement, just a little reminder. So you take a poset and you take an element of this poset, and the toggle action at X will be a transformation from ideals to P of P over ideals of P, sorry, as it follows. So if you have your ideals, you just check if you can add it. And if you can add it, because this element is not in the ideal, and if you can add it and still have an ideal, then you add it. If the element is in the ideal, and you can take it out and make sure that if you take it out, you still have an ideal, then you take it out. And otherwise, you do nothing. So these are toggle action, and some remarks. First, it is an involutions. Sorry. So each toggles are involutions, and two toggles are commuting if and only if one. So if you toggle at X and at Y, you need to avoid that X cover Y or Y cover X. Okay, so I need to avoid it. That's the only thing I have to check to make sure that the toggles commute. And now here's the definition of a Creveras complement. So again, take your C, your coxet element. Then you take the Auslander right hand quiver. You will see an example just after this slide. Okay, so just take the Auslander right hand quiver of C, and then you take a reading of your Auslander right hand quiver. So you take a reading from the minimal one, so from the left to the right, respecting the order of the Auslander right hand quiver. And the C Creveras complement can be defined as a sequence of togglings, okay, following a reading of the Auslander right hand quiver. Okay, so some remarks following this statement. So the transformation Creveras is well defined because it doesn't depend of the reading of the Auslander right hand quiver, because it comes from the things I said before, like the things that explain when two toggles are commuting. Okay, so they are commuting exactly when you change the reading. So that's pretty nice. Another thing, because for some of you who have already saw things about this research in the CAAC with my poster, I explain it in another way, and the other way is to take the C sorting word of W0, where W0 is the longest element of SN. But here I will not explain how to calculate it, but it's really there is a really nice link between the reading of the Austrian right-hand quiver and the C sorting words. So that's really if you don't really understand the Austrian right-hand quiver, you can at least maybe for some of you understand the C sorting words. And another thing to say is the name. Why Croveras? That's because it is a play of words, like a fusion between Croveras, because we want to make things linked to Croveras first, and with row motion, because row motion can be defined as a sequence of togglings, like we define Croveras. Okay. That's a play of word of Nathan Williams, for those who know how Nathan Williams works. So he loved play of words. So he suggests this name, and that's we say okay for that name. So here an example. So you take n equals 4, Coxeter element, just not so easy, but an easy one, 1, 2, 4, 3, and you write it as okay, so adjacent transposition project. And here is this oscillator right-hand quiver of the element C. Take a reading of it. So you have 3, 4, 1, 2, 1, 4, and so on. Okay, 1, 3, and so on. So take a reading, and this, the Croveras complement, will be defined as the toggling sequence given by this reading. And then below, you can see all the orbits given by the Croveras complement, and you can check. Maybe I don't know if I have time, but we can just check, for example, the easy one here, just by seeing that first you have to maybe I make sure that I will not make, yeah, okay. So first you toggle at 3, 4, 3, 4, it disappeared, then 1, 2, it disappeared, and then all the other things until 2, 3 will not be added, because we will not have ideals, because 1, 2, and 3, 4 are already disappeared. So you still have 2, 3, and then 2, 3 you toggle at it, you had nothing. Okay, so that's one way, and then all the orbits. And if you if you used to work, sorry, with Croveras complement, you can see that the orbits can correspond to orbits you can have for non-crossing partitions of SN, so S4. So that's how we go to the charming bijection. So the charming bijection, just first I have to explain some vocabulary before stating the main results, and then explaining what is the charming bijection. But so the support of a non-crossing partition is the set of adjacent transposition we need to give a reduced expression of the permutation pi. And the support of the non-nesting partition nu is the set of simple roots appearing in the ideal. Okay, so all the minimal elements appearing in the ideal, that's the support of the non-nesting partition. And so the theorem says that there exists a collection of bijection indexed by the Coxeter elements, C, such that first so you can see that the Croveras complement is preserved by just commuting with the charm bijection, and the support is also preserved. And another thing I have to say, because I didn't have, I saw that I didn't mention it in the statement of the theorem, but it is unique under these two things you have to respect. Okay, so if you have these things to respect, and you want to have bijection between the two, so non-crossing and non-nesting, then there exists a unique collection of bijections that satisfy that. So now I will try to explain how the charming bijection works, and to do that, I will bring a bit of love here. So I know that Saint Valentine's Day was 1 month before, but yeah, Nathan makes a joke by saying that we must put the paper at Valentine's Day, but that's okay. So the definition of a charmed root. So you have your Coxet elements. You take element ij, and it will be said to be seam charmed if either I is in the left part of C and J is in the right part of C, or the inverse. So I is in the right side and J is in the left side. So here under that you have this example, and you can check, for example, 2, 7. 2, 7, you can see that 2 and 7, okay, 2 is in the right part, 7 is in the left part, okay, and so on, okay. So there are a lot of other ways to characterize charmed roots. So first, you can see it thanks to the quiver. So ij will be charmed if the 2 rows here are oriented in opposite directions. That's pretty nice. Another way, but I will not explain it more because we need to have more tools in representation theory, but we can use it to characterize charmed roots again. And another way, more combinatorial, is to see it thanks to the geometric model we use for the C non-crossing partition. A root will be said to be C-charmed if and only if the diagonals ij and I-1, j+1 are crossing. So yeah, you have two free crossings, which cross, 1, 4. So 2, 3 is charmed, but 2, 8 is not charmed, and you can check it. 2, 3 is charmed, and I said 2, 8 is not charmed. Okay. There are a lot of other ways again, but I will not explain all of them. But here are some nice things you can use more combinatorially. That's pretty. I think that's pretty nice. And now I will explain the bijection through an example. Okay. So again, take the Coxet element, which was less easier than the other one. You take again the non-crossing partition we saw before, and here to construct the ideal we will use. So again, it's a definition from Nathan. So taking intimate families of lattice paths. So what it means, you will draw lattice paths such that there are some rules for this lattice path, but I will try to explain it here. So first, you put little things, so little dots, let's say, at each element corresponding to the non-crossing partition, and you can see that there are some starting at 6, for example. There are 1 starting at 6 because you have 6 to 8, okay, in the same block, and so on. So you put this thing, and then you will draw the smaller dig paths you can draw in the poset, okay. And you have some rules to do that, but here they are not so difficult. First, you draw just the smallest. So for the 2 first dig path, this part. Oh,
you have lost your connection again for a few seconds.
Yeah, again, that's a call because I'm connected to my phone. That's
okay.
Sorry. Okay.
So maybe you're
again. So I'm trying to explain how to construct the path. Okay. So first 2, 6, you draw the smaller one. You can draw here. Here between 3 and 6, there is something to say, because you can ask why I don't go to the earth below here. That's because there is this rule saying that if you go down to this earth, then you need to have a lattice path, a path going up to this earth. And here you have nothing starting from 4 or 5 to draw another path going through this hurt, so going up and down. So you can't go down and up. That's one of the rules you have to respect to draw this path. And another rules, you can see it for the last thing. So again, the dig paths I draw is are just the smaller dig paths between like an open bracket and a closed bracket. Okay, and the last pair I have to join. You can see that this path, so I can go down to the earth because I don't have lattice below to this hurt. Then the second one, same thing. And here, this rule works. You have a path going down and going up, and another path going up and going down to this hurt. So you can draw this lattice path going down to this hurt and going up again. And that's the same thing for 6 and 7. Okay, at this lattice, this point here, the lattice, the path going down and going up and down exists. So you can go down to this hurt and going up afterwards. So you have the right to, let's say, kiss between, to have a kiss between some passes, but you don't have to cross them between. Okay, just only on they will kiss, so they will touch each other at each hurt, but they will not cross like you can see here. So here you can, so yeah, there is a difficult part in it because here I just try to explain the way you construct the ideal from the non-crossing partition. And the difficult part is to get back the non-crossing partition from the ideal. And here you can see all the rules you have to respect for the lattice path. And so all the rules you have to respect locally, because there are local rules, in fact, at each point of the poset. And so you have to respect all the things on the right side, but not the things on the left side. So the rules saying that you have a path going down and going up, but no path going up and going down to this earth is forbidden. Okay, so the rule that is forbidden. Okay, and so I will now try to explain from an ideal how I can get back this intimate families of lattice path, and from that I can get back the non-crossing partition. So first, I take the biggest dig path I can draw in this ideal. So the biggest included in the ideal. Okay, so that's why I have this path going this way. Okay, and then because of the rules saying that if you want to go to this hurt, you need to have a path going up and then going down. So then, sorry, just to make sure that I'm not mistaken. But yeah, there's some, I try to explain, but there is something saying that if you had, so that's the way I have to say it. If you had a path going up to so from 2 to and going down to 3 to this earth, okay, then the lattice will be different because you will need to go down here and then go up here, because again the smallest, you have to draw the smallest lattice path and so on. So that's a way to explain why we don't care about these hurts anymore, because they are just below the lattice. And if there are paths going here, then if we go back to the rules I explained before, you need to go down to the earth for the biggest lattice and then going up from the earth. So that's why we don't care about it. Just the only thing we care is below this earth, because here you can kiss the earth, above here. So you do it. Yeah, you can see here. And that's the same thing for the elements here below 6 and 7, but there are nothing below, so you just draw the easiest lattice path you can draw, and you get back the intimate families. Okay, I hope it's a bit difficult to explain how it works really well, but I try to do it. I hope I at least give you some points about this. So now I will try to explain how we give the proof of this. And here you have the thing. So the figure we saw in the beginning is just the trapezoid you can see here on the left, okay, or on the right if you change the Coxeter element, okay, and all the other rows are something linked to the strategy of the proof. So we want to do to use an induction proof, and more precisely, we want to use a Cambrian induction. So first, we want to prove the statement for the easiest Coxeter element, that is the cycle from 1 to n, and this is already a result known from Stryker and Williamson in 2012. So we use it, and then to do the Cambrian induction, you fix a Coxeter element, and you will conjugate this element by an adjacent transposition that will correspond to a sink in the quiver. So it's initial transposition, if I didn't say things wrong, but yeah, you do like things like that, and these arrows correspond to the action you will have just by conjugating C with this simple element. Okay, just in the quiver, saying that from C to C prime is just changing a sink to a source. Sorry. Okay, like something for some of you who already heard about cluster algebras, something we used to show in this field. So here again, the same figure, but with an example. So you have the partition we begin with. He is all above on the right, okay, and all the square is on the right or on the no. Sorry, I'm saying wrong. So it's more on the left center. So the cycle I'm just around it here, and so you have, I already explained the Krover-Haas complements, okay? I explained the Krover-Haas complements. Then I tried to explain the Chan bijection in the example given before. So here, and you have the result here. And then you can see that for a non-crossing partition, going from C to C prime is pretty easy, because here you can see that there are two labels that are exchanged. So I try to find them, but it's 6 and 7, yeah, 6 and 7, okay? So you can see that 6 and 7 are exchanged. So we just conjugate by 6 and 7, and that's pretty easy for a non-crossing partition. But for a non-nesting partition, that's messy, a bit messy. But thanks to the Auslander right and quiver, we can see it as the sequence of togglings following. So maybe I will try to, I will just check the time. Okay, nice. I will go back to the Auslander right and quiver. So sorry, I will go quick. Where is the Auslander right and quiver? Yeah, okay, nice. So the Auslander right and quiver, to get the sequence of togglings we will use to go from a non-nesting, from one non-nesting partition to the other, you start from 6, 7, because we conjugate by 6, 7, okay? And you follow the rows straight up and right, okay? And straight down and right, okay? And you take the elements appearing following the order. So you will toggle first at 6, 7, then 6, 5, 7, sorry, 2, 7, and so on till you get everything here. Then you toggle at 6.9, sorry, then 6.8. Okay, and then there is something a bit technical thing. Let's say you will toggle. Oh, sorry, you will toggle back at 6.7. So you toggle at 6.7, then you follow the arrows, and toggle again at 6.7. So I hope. So thanks to the Ostender right hand quiver, we can really explain how to go from this non-nesting partition to this non-nesting partition. So maybe we could, not sure I could try to do it now, but maybe you can see that some elements following, so 6.7, maybe 6.7 is the easier one. So 6.7, if you toggle it, it doesn't change anything. And then you will follow, so it's like you will follow the togglings here. If I remember well, you will follow the toggling, so maybe on the left, you will follow the togglings, first going up at the vertices that are charmed vertices. So you will toggle first at the hertz, and then you're going down by toggling on all the other vertices. So we toggle, if I don't do things, I'm sorry, it's the inverse, that's the way it works. So first you toggle at Earth going down to up, okay, so you will have the Earth added, okay, and then you go down by toggling. So you toggle here, you will have nothing, and so on. Okay, you toggle here, you will have nothing, and that's the same thing. If you go that way, you're going up first, toggling at the hertz, and so toggling. No, sorry, you go up. It's here. You go up toggling at the hertz, but there are no hertz. So then you go down, and by toggling, you will get rid of this vertex. If I don't say things wrong. Okay. So I try to explain it because I have time, but hope I try to again, I succeed to give you some things to understand. So corollary, I maybe have make a mistake, but that's fine. So you can have that the Krover-Haas complements have the same order that the Krover-Haas complements, because we have done all the things to make sure that the Krover-Haas correspond to the Krover-Haas complements. And this result here is explained in type A, but we can extend it for type C thanks to some symmetry, central symmetry for non-crossing partition, and an axial symmetry for non-nesting partition. And we can obtain type B from type C, but it's not so easy because, yeah, we used to have in mind that the poset, the root poset for type B and type C are the same, okay? But the action of the Krover-Haas complement will be different. That's the point here, because last time I talked about it, I'm just mind about this, and yeah, the only thing that changed a bit is the Krover-Haas action, and then the Krover-Haas action just make things working different between B and C. So that's why it's not so easy to have B from C, but not so difficult either. So that's the point. But we don't have already the result for type D. And that's one of the questions we can ask at the end of this talk. So I try to stimulate you about this bijection between C non-crossing and C non-nesting partition, sorry, depending of under an action from a Coxeter element. And now we can ask if we can have the same thing for type D. I have some ideas, but that's still difficult. I have done the calculation for D4, and it works pretty well, but we don't really understand how. So we can make things, let me try to explain. We can make things coincide a bit with what we saw for type A and type C and type B. But it's difficult to say how the lattice path goes, because here, if you have a picture of type D, I'm used to show the picture of type D like two followers, okay? you have two floors. First, a triangle type A and a triangle type A, but just rotated a bit. Okay, so 90 degrees rotated. Okay, and if you saw like that, if you want to give an idea of this poset, is not so easy, because it seems not so easy to say that a poset will be defined by lattice passes, because you need to do dig paths that go up to the second floor, and that's not so easy. But we can make at least things coincide with what we saw for type A, just by seeing what's going on for the triangle at the bottom, and make things coincide. So that seems promising, but we don't have for the moment something really concrete. Then maybe we can try to introduce a global theory containing at the same time the classical row motion, because as I explained here, pro-Voraz complement is defined as a sequence of togglings, but maybe we could imagine something where we just apply togglings in the ideal in either way, maybe considering some kind of group of the togglings, I don't know, but and the group of togglings maybe can be generated by the element, and I don't know, but that could be an idea to go further in this thing. And yeah, there are some questions, because as I said before, non-crossing partitions are linked to some little things in representation theory and theory of algebras, and we can maybe ask some question from this bijection, because it is a bit new of bijection. It is a new bijection, so it's maybe we can try to explore a bit more. So yeah, things have to be continued. And so I will stop there. Thank you for your attention.
Let's thank our speaker. Are there questions? Okay, so maybe I start with a question. You've already answered some of my questions. The classical question, what about other types? But I do have another question. So you told us that the square of the Cravaras complement is rotation. Is there some nice thing about the square of the Cravaras complement then? Because the non things you could still rotate in some sense.
We didn't see it like that, because we in fact we go right straight to the ideal point of view. I don't want to say any mistakes, so I don't know. I will say I don't know, but maybe I think that would be nice to see if there is something related, like rotation. Yeah. I'm pretty sure that there is something, but I don't want to say something wrong. So.
Okay. Yeah, thank you. Further questions? Okay, I do have more questions. So if no one asks questions, so are there some other nice statistics that are preserved by your bijection?
For the moment, we don't explore it yet. Well, yeah, this is something we need to go through. I think that could be nice, but we only try to explain this bijection motivated by result from Armstrong, Stomp, and Thomas. I don't remember exactly the year, but it's a result saying that it just saying the motivation behind also that they have a bijection between non-crossing partition and non-nesting partitions, respecting the row motion, so the row motion action, and from this idea, some people, so I think it's Gabriel, who asked first that maybe we could try to, because it was between non-crossing partition, classical non-crossing partition, and non-nesting partition, we asked about the action of C in this thing, and that's how it starts. But yeah, we didn't explore that much, I think, and we need to explore more. So yeah, maybe statistic things could be a nice thing to do. I don't have really any answer because we don't don't see it more, but yeah.
Okay, thank you.
You're welcome.
Are there more questions from the audience? Okay, so if not, it's time to thank our speaker again. And we can
Thanks to the organizer again.
Yeah, and we can stop the recording.